Welcome back everyone. In this video we're going to be finding the derivatives of certain inverse trigonometric functions. In particular we're going to be finding the derivatives of sine inverse of x and tangent inverse of x. And just a little bit on notation before we actually get into it is that sine inverse of x can also be written as arcsine of x, and tangent inverse of x can be written as arctangent of x. And they mean the exact same thing, it's just different notation written a little bit differently. And an important thing to keep in mind is that sine inverse of x is not the same as sine of x to the negative 1. The function on the left, sine inverse of x, is the inverse of sine, whereas sine of x to the power of negative 1 is 1 over sine of x. And we are not going to be looking at the function on the right, we're going to be looking at the function on the left. This is an inverse function. Before we get to the calculus part, I want to make sure that everyone knows how these inverse functions actually work. And sine inverse of y, if that's equal to some number x, that's the same thing as sine of x being equal to y. When you see sine inverse of something, it's really asking a question. And that question is, what's the angle x such that sine of x is equal to y? And whatever that angle is, would be the answer to what sine inverse of y is. As an example, sine inverse of 1 is pi over 2, because sine of pi over 2 is equal to 1. Now there's an issue with this, because you could argue that sine inverse of 1 could also be 5 pi over 2, because sine of 5 pi over 2 is definitely equal to 1. And so which one is it? Is the answer pi over 2, or is it 5 pi over 2? And we need to resolve this, because if we don't, then sine inverse is not a function. Part of being a function is whenever you plug something in, you get exactly one answer out. And right now we have two answers, and there's actually infinitely many if we don't do something about it. And the way we're going to resolve this issue is by restricting the range of sine inverse. And all that means is that we're going to restrict the possible outputs so that you can't get more than one output for any given input. And what we're going to restrict it to is from negative pi over 2 to positive pi over 2, including those endpoints. And this will make it so you can only get one possible output for every input. And while we're on this topic, the domain of sine inverse is negative 1 to 1, because those are the only possible outputs of the sine function. But now that we've restricted the range, if we return to the question of what sine inverse of 1 is, it's equal to pi over 2 and only pi over 2. Any other possible output would fall outside of the range, and so those are not eligible. Now tangent inverse is a different function, but it presents the same sort of issues of possibly getting more than one output for every input. And we restrict the range of tangent inverse to negative pi over 2 to positive pi over 2, but this time not including the endpoints. Now tangent is a little bit of a different function than sine, and tangent inverse does not have the same restriction on the domain, and tangent inverse has a domain of all real numbers. Now of course we're in a calculus class, and so we have to ask what is the derivative of both of these functions. And I'm going to start with tangent inverse because it's a little bit more straightforward to work through. And the way that we're going to find the derivative is actually very similar to how we found the derivative of natural log. We're going to start with an identity that we know to be true, and then we're going to take the derivative of both sides and do some kind of clever manipulations until we get the answer. So we're going to start with the equation tangent of tangent inverse of x is equal to x. Tangent and tangent inverse being the inverse of each other have this nice property. Now if I switch the order on those two functions and take tangent inverse of tangent of x, it's a little bit trickier, but we're not going to explore that idea in this course. Now let's take the derivative of both sides, and on the left side we're going to have to use the chain rule because this is tangent of tangent inverse. The outside function is tangent, and the inside function is tangent inverse. And using the chain rule, the derivative of the outside, the derivative of tangent, is secant squared, but this is secant squared of the stuff on the inside. So this is secant squared of tangent inverse of x, and then you multiply by the derivative of the inside, and the derivative of tangent inverse, well, we don't know what that is, that's the big question here, and so we're just going to leave that as the derivative of tangent inverse of x. And then on the right side, we know that the derivative of x is 1. And from here, let's move the secant squared of tangent inverse of x over to the other side, and now in a sense we've actually answered the question, that being the derivative of tangent inverse of x is equal to 1 over secant squared of tangent inverse of x. And while that's correct, let's see if we can make it a bit more presentable by doing some further manipulations. And one thing you might remember from your pre-calculus course is that secant squared is equal to 1 plus tangent squared. And so secant squared of tangent inverse of x is equal to 1 plus tangent squared of tangent inverse of x. And much like how tangent of tangent inverse of x is equal to x, tangent squared of tangent inverse of x is equal to x squared. And so now we have an answer that's a little bit easier to digest. The derivative of tangent inverse of x is equal to 1 over 1 plus x squared. Now, if you're looking back at this process and it seems intimidating, don't worry, we're not going to ask you to repeat this. It's just so that you know where these things come from, because I always want you to know where everything comes from, whether it's from me or from a different source, so that it's a little bit easier to believe and doesn't feel like it's fallen out of the sky. Now let's use this rule in an example. And I left the rule in the top left-hand corner in case you forget it. And let's find the derivative of arctangent of 3x plus 1. And don't let the arctangent scare you. That's the same exact thing as tangent inverse, just with different notation. Now finding the derivative of arctangent of 3x plus 1 is going to require the chain rule, with arctangent being the outer function and 3x plus 1 being the inner function. And we know that the derivative of arctangent of x would be 1 over x squared, but there's not an x on the inside, it's 3x plus 1. And so the derivative of the outer function is 1 over 1 plus not x squared, but 3x plus 1 squared. And then as always, when we're using the chain rule, we have to multiply by the derivative of the inner function, and that's the derivative of 3x plus 1, and the derivative of that is 3 plus 0. Next, let's talk about the derivative of sine inverse of x. And the proof for this one is the same idea as the derivative of tangent inverse, and so I'm not going to repeat it because you already have a sense of where this rule would come from if you wanted to find it. Now, the derivative of sine inverse of x is equal to 1 over the square root of 1 minus x squared. And let's use this to find the derivative of sine inverse of cosine of x. And once again, this is a chain rule problem with my outer function being sine inverse and my inner function being cosine of x. And the derivative of that outer function, sine inverse, is 1 over the square root of 1 minus not x squared, but cosine squared, because that's the inner function. The inner function is cosine, and so we need to plug that in for where we would normally put x. And then with the chain rule, we have to multiply by the derivative of the inner function, which is the derivative of cosine, and the derivative of cosine is negative sine. And so the answer as to what the derivative of sine inverse of cosine x is 1 over the square root of 1 minus cosine squared multiplied by negative sine of x.